The topic of this course is organic chemistry, and I think that it's appropriate that we first define this subject before we get any further. And in context of modern chemistry, organic chemistry is nowadays defined as carbon compounds chemistry. In other words, chemistry of carbon compounds. And this definition, although very brief, immediately raises two questions. The first one is, why carbon? Why is carbon so special as to deserve its own branch of chemistry? And the second question is, well, if it's already chemistry of carbon compounds, why is it called organic? Now, the answer to the first question lies in the fact that carbon has a property which no other element in the periodic table shares, and that is, it has an ability to form seemingly infinite chains composed solely of carbon. In other words, it can bind to itself, unlike other elements in the periodic table, and it can bind to itself in many different arrangements. So it can form these linear chains. These chains can be branched. They can contain other elements. They can even contain cyclic subunits, etc. And clearly, this very quickly then leads to a huge diversity of structures. So today, about 25 million organic compounds are known, which means that they have either been synthesized in lab or isolated from plants and animals. The question, why is it called organic, is rather historic. The word organic comes from the word organism, which is traditionally associated with plants and animals, because organic chemistry used to be associated with compounds that were isolated from plant and animal material. Actually, in the 17th, 18th, and early half of the 19th century, there was a very powerful school of thinking which assumed that there is such a thing as vis vitalis, which means life force, that exists in plants and animals, but not in rocks or water or dust, and that this vis vitalis is responsible for the generation of organic compounds. It turned out that this notion was incorrect, and it was proven to be incorrect in 1828 by German chemist Friedrich Wöhler, who did a very simple experiment. He took ammonium isocyanate, which is an inorganic salt, and then he heated it. And he managed to isolate urea, which even at that time was classified as an organic compound. Now, this clearly has proven that there is no such thing as vis vitalis, because otherwise this conversion from something that is dead and has no vis vitalis into something that does have vis vitalis would not be possible. And many people view this experiment as the beginning of modern organic chemistry, because it has really proven that organic compounds are not something that nature gave us, but also something that we can synthesize ourselves. Now, all organic compounds have one characteristic in common, that is, they contain carbon. However, there are some compounds which do contain carbon, such as graphite or diamond or carbon dioxide or sodium cyanide or many carbonates. So all of these compounds contain carbon, but they're still classified as inorganic. And the reason for that comes from the fact that their properties make them more inorganic. So some of these, for example, are salts, so they're more easily analyzed with other inorganic compounds. This is a little bit counterintuitive, but it's very widely accepted, so we'll stick with it. So we will not talk about these compounds, but we'll talk about organic compounds in general. And I'll give you now a couple of examples of compounds which you must have encountered in your everyday life. One of them, one that I'm just drawing now, is something that you should consume daily, because this is the structure of vitamin C. And vitamin C, as you probably know, can be found in lemon or kiwi as well as many other fruits and vegetables. Unlike vitamin C, the compound that I'm drawing now, you should probably not consume every day or at all, because this is the structure of morphine. It's a relatively complex molecule. And morphine is typically isolated from opium poppy, and it's one of the most potent painkillers known to men. However, the problem with it is it's highly addictive, and therefore it's not used in medicine at all except for very sick terminal patients. Another problem with morphine is its isolation. Since it's isolated from opium poppy, opium poppy has to be harvested, and opium poppy grows in regions such as Afghanistan, which are politically very unstable. So it's very difficult to get a stable crop through legal channels of this plant. Now, not all organic molecules have to be very complex. This is a very simple molecule, just a handful of atoms, and it's acetic acid, which comes from vinegar and gives vinegar its characteristic acidity and taste. A related compound is shown here, and it's called butyric acid. And butyric acid gives stale butter its unpleasant odor. I'll finish with one more example, and that is a molecule that you probably heard quite a bit about in various TV commercials, and that is cholesterol. And here is its structure. It has a lot of rings. And the thing that TV commercials don't tell you is that both good and bad cholesterol have the same chemical formula. It's just their fate in the bodies that makes them good or bad. Now, the story doesn't really end here. It's just that this board is too small and we don't have enough time, but many other molecules much bigger, such as proteins or DNA or sugars, for example, are all organic compounds. And furthermore, I've shown you here all the compounds that come from natural sources, but there's several compounds, well, there are many compounds, such as Teflon or polyvinyl chloride or polyethylene, which are made by man synthetically. So these are so-called synthetic polymers, which do not occur in nature, but are still organic compounds. And the result of this little discussion is that organic compounds are literally everywhere, and this is certainly much more than a cliche. Either they come from natural sources in our nutrition, in many of our clothing items, or they're synthetically produced in cases of plastic, food additives, dyes, etc.